Complete the following synthesis while avoiding mixtures. Turns out there is two ways of doing this, but I'm going to show you the best way, because the other way, the opposite direction I'm going to show, we have to use a reagent that's not introduced in most organic chemistry textbooks. Alright, so the one we're going to apply is actually taking advantage of the fact that this is an aldehyde and that's an aldehyde. We're going to end up saying it's the same aldehyde. So this alcohol is what's going to get this substituent added onto it. Right. Can't do that directly to an alcohol, but I can to a carbonyl. So the very first thing I'm going to do is think about turning that into a carbonyl. But what I want to do first to make sure I have an aldehyde still when I'm done is to protect that aldehyde. So I'm going to use a diol with a little bit of acid to create a protection group on that carbonyl. So we have O, carbon, 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 O, back to that, protected, and this is still an OH. Alright, now I need to reduce that and have it so I can attack the backside of it. That'll work best if it is an aldehyde. So I'm going to react this now with some PCC. Move my pen up so I can write a little bit better now. Alright, so I still have that carbonyl, that ring. I still have the protection group on here. But this other alcohol is now an aldehyde. Alright, now I'm going to add this R group on there. So that's a CH3, CH, CH3. Just this thing right here. And I'm going to put that on a Grignard. I'll put it in some ether. And that should easily enough go on backside of that carbonyl. So that's still intact. Ring has been left alone. And this is an OH with that H still on it, but now I have a CH, CH3, CH3. And to turn this into that, I just need to remove my protecting group, which I can do with some HCl. That'll kick that back off into a carbonyl. So technically the molecule is flipped from left to right. I would probably have seen this a little bit easier had I bothered to draw that original structure mirrored. To draw attention that you probably should try to add the R group that we're adding to the alcohol rather than the aldehyde. Alright, that is the answer I was expecting. What I'm going to do now, go erase all this, and we're going to essentially, the molecule is going to stay left to right. So we are going to end up putting the R group on this side and then reducing that back to an alcohol. Alright. See all the problems associated with it, which is why if you were probably doing on a test, you'd probably give up on this way relatively quick. Alright, so the very first thing we're going to do is add that exact same R group on as a Grignard. So that's with some ether. And that is going to leave this thing mostly intact. Let me start this drawing with that ring. This O will now be an OH. It'll still have an H, but it's now going to have a CH with a CH3 and a CH3. So we've technically turned the left side into what we wanted on that final product. So our goal now is to oxidize just the aldehyde. But unfortunately I can't do that. I don't really have a good way of oxidizing a primary alcohol and not a secondary alcohol. So if I put NaOCl-CH3 and target of avoiding mixtures, I'm going to have to realize that I'm going to get a carbonyl over here with the R group we want. Add an R group over here. Now, technically, what I'd like to do now is oxidize, or reduce a ketone, but not an aldehyde. And we don't have anything like that presented in most organic textbooks. Can't do an aldehyde, can't even reduce an aldehyde and not a ketone, even though an aldehyde is typically more reactive. But out in the literature world, cesium, along with our BH3 or BH4, will actually do that. It has a nice little property where it will indeed reduce a ketone but not an aldehyde. So in that case that could work, but we have to put a big huge box around this because that's not in almost any organic textbooks. So this is probably where, had you tried this step, you would have to quit there or write something and hope that your professor accepts that you are going to end up with a mixture of some oxidized ketone, some oxidized aldehyde, and some reduced. So you never get perfectly this, but apparently the cesium tetraborate will.